And also, is it okay if people will ask you during talk, or you want everyone to keep questions to the end?
No, absolutely. I'm happy. They
Oh, good.
talk. You can.
What did he say?
Oh, so can you? Is my audio okay?
Well, what did you say? You don't want questions until the end?
No, questions throughout the talk is perfect.
Oh, that's fine.
Okay.
Is my audio okay? Just testing, testing, testing.
Yeah.
Is that a bit better? I'm increasing the input volume.
Alexei, I am a co-host.
Yes, you're the co-host, yeah.
Co-host, because I don't see the list of participants. I don't know. It's very strange. In how many people we have now?
There are 20 participants. 21.
Maybe we will start in 1 minute because people arrive last minute.
Yeah, absolutely.
Okay, maybe we can start. Could you please show your presentation even? So, hello everybody. Let's start our seminar. Today, we have a pleasure to have a talk by Ivan McDonough. He will tell us about very interesting stuff like dark matter, inflation, and gravitational particle production. Okay, 1 hour, please.
Okay, thank you so much for having me here today. Thank you for a kind introduction. It's great to be able to talk with you. It's such a wide audience. I think it's amazing that you're continuing to do this online seminar series, reaching out to people all over the globe. As was mentioned, my talk today is about dark matter, and in particular, I'm thinking about the production, sort of the origin story of dark matter within the context of inflation. This is part of a research program, research direction that I started and got involved with as a postdoc back in 2021 at the University of Chicago. Now I'm a junior faculty member at the University of Winnipeg in Canada. And this is based on really a collection of papers. And I think we should be able to keep this all to 1 hour. And as I mentioned, I'm happy to take questions through the talk. You're welcome to harass me and we can try to argue it out. And then if I think we're really running short on time, I'll just keep on moving. Sounds good. Okay, the plan for today is one, to just think about cosmic inflation as a particle factory. And our universe is filled with dark matter, which is presumably a particle, although maybe a primordial black hole. It's filled with regular matter. All of this stuff had to come from somewhere. We usually think about reheating as the genesis of all things, but there are, within this scope of where did all the matter in the universe come from, there's more possibilities. And in fact, one minimal and very non-thermal possibility for the origin of in particular dark matter is cosmic inflation. And then I'm going to focus on 2 case studies, which I think are illustrative of the general types of physics which can go on here and why this is an interesting phenomenon to really dig into beyond just the surface level. And then I'm going to finish with some open questions. All right. So let's get started. Cosmic inflation as a particle factory. And I'm going to try to make the point here and throughout the talk that this phenomenon of particle production just through the non-adiabatic of space-time, non-adiabatic expansion of space-time, what we sometimes call gravitational particle production. I'm going to argue that it's simple, it's minimal, and it's ubiquitous. So in many different model contexts, this sort of pops out at you. So I guess the starting point for what's become a very hot topic in the last 5 years or so is the idea of the cosmological collider, which is that we have this beautiful CMB. And in fact, insofar as we believe that the fluctuations in the CMB and the C-square structure came from quantum fluctuations during inflation, we have the ability to probe all particle species that were around during cosmic inflation and scattering events, exchange events. All of this structure of quantum field theory during inflation is encoded in cosmic microwave background. And in particular, one of the primary aims of this cosmological collider program is searching for signatures of new particles in the CMB non-Gaussianity. Many authors have worked on this, including myself, thinking about higher spin fields and higher spin supersymmetry, which I'm happy to talk about another time. A slightly similar but distinct direction to take particle physics and inflation is to think about inflation as a particle factory. And the basic idea is that the expansion of space itself can convert quantum vacuum fluctuations into particles, into on-shell particles. And the precise state here would be at asymptotic late times. And this is something that's already operating sort of under the hood of inflationary perturbations all the time. We don't usually phrase it in this language. The simplest example is just to take some spectator field, and here I'm saying it's conformally coupled to that. I just have this very, very simple dispersion relation for some field in an inflationary background. If I just plot out what we call the adiabaticity parameter, omega k dot over omega k squared, it's peaked about the time that this mode exits the horizon. You have a violation of adiabaticity in your quantum field theory as this mode is exiting the horizon. And there's a precise formulation of this. You can find it in, for example, a textbook by Burrell and Davies, that if you start with a negative C mode, like the Bunch-Davies vacuum state, and you evolve towards late time, what you in fact find is you have a combination of positive and negative frequency modes, or you can think of it as the two Hankel functions of your cosmology at late times. And these coefficients, alpha and beta, we call them the Bogoliubov coefficients, and in particular beta, this beta parameter, tells you how many particles you've produced. And we're going to dig into this more and more as the talk goes on. So don't worry if any of this is new to you. Question from Philip?
Yeah, could you just remind us what eta was?
Eta is conformal time.
Oh, thank you.
So we have inflation as a mechanism to produce particles, and that's on one hand. On the other hand, here we have dark matter. And in particular, I think it's important to emphasize, and I try to do this in every talk that I give, that the strongest case of dark matter comes from the cosmic microwave background. And if you just take the Planck 2018 measurements even from TT, the temperature anisotropy power spectrum, and you look at what is the constraint on omega dark matter, the abundance of dark matter. And it differs from 0 at greater than 70 standard deviations. So, the CMB demonstrates the existence of dark matter, to greater statistical significance than we know almost anything else about the universe. I'm more certain that dark matter exists than I'm certain I'm going to wake up tomorrow. Let's put it that way. So this connection between inflation and dark matter is put together in the late 90s, starting with Rocky Kolb, Antonio Roto, and Dan Chung, and then many other authors around that era. And this is sort of the simple story that was put together. I'll mention that these nice plots were actually made by undergraduate student, at the time now master student Guillaume Peyer, master student with me, and Robert Brandenburger now. This is the simplest conceptual story of how you can get dark matter from a scalar spectator field during inflation, which is I have some dispersion relation and I can plot it. And you can look at this adiabaticity parameter. It's peaked around here. This is A over AE. AE is the end of inflation, tends to 0, meaning 1. It's peaked around the end of inflation. So this mode is undergoing some non-adiabatic evolution at the end of inflation. If I solve the equations of motion for this field, it's essentially just a Klein-Gordon equation with this dispersion relation, and I calculate these Bogoliubov coefficients, I can calculate a particle number. And I do this this is for a single mode co-moving wave number k. I do this for all k. I integrate over k to get the total number of particles produced, and then I can calculate the abundance of particles, the density in particles at late times. And what I'm showing on the right here is contour plots, where for different reheat temperatures of the universe, I can, which is a proxy for how much expansion happened between inflation and today, I can get the right relative density of dark matter along each one of these lines. And this is in a plane of mass and conformal coupling. You may follow these lines up, I can get up to the minimally coupled scalar, but this non-minimal coupling really opens up the parameter space. And that's sort of the story of dark matter production from inflation insofar as gravitational processes are concerned. You have this interplay between just production of just from the mass and also from this non-minimal coupling. So fast forward to the present day, and gravitational production sort of operates at the frontier of dark matter phenomenology. And there's lots of interesting new models, some of which are proposed by myself, that can have gravitational production operating in the background or in the foreground. So an example is one paper I wrote with Azadeh Mahmoudjad, thinking about pions actually make a great axion-like particle. If you have a dark sector where the pion is stable, say there's no photons it can decay into, there's no weak force, there's no electroweak force, pions can be axion-like particles. And if I have these stable pions, I'm also going to have stable baryons. And it turns out that if the pions are really light, the baryons are really heavy. And the baryons turn out to be a great super heavy dark matter candidate that can be produced through exactly this gravitational processes during inflation. Another example of a relatively recent model, and I should mention that this scenario of higher spin fields, I'm talking, a spin 5 particle could be dark matter. There's a couple other works by other authors also proposing this, but here I'm focusing on a paper by myself and Leah Jenks and Stefan Alexander, where we looked at gravitational production of these higher spin fields and just the proof of principle that you can constitute all of the abundance of dark matter just through these gravitational processes. And there's some assumptions that went into when it's calculating this, but I can get into that another time or later. And finally, also at the model building frontier of inflation is gravitational particle production. So in particular, a paper I had with my now master's student, Guillaume Peyer, and along with Rocky and Andrew Long, we consider inflation models that sometimes they're referred to as rapid turn models, but I'd say the key conceptual point is that these models are motivated by its inflation on a steep potential, that V prime over V is bigger than or equal to 1. This is motivated by swampline conjectures, the Sitter swampline conjecture. We considered different models and considered in the context of these models, can you get the right relative density of dark matter? And it turns out that in one sort of broad class of models, known as hyperinflation, is not possible. And whereas in other types of models, we refer to them as monodromy inflation, but it's really a class of models proposed by Anna Achikara and collaborators over the years. Everything checks out. And we can get into more detail about this, but it has to do with matching CMB observations for NS and AS while also matching the relative density of dark matter. It turns out that one of those things needs to go in hyperinflation, whereas monodromy can get all at once. Okay, that's sort of my lightning introduction to gravitational production. Now let's get into a couple case studies. And the first one is a paper that came out a few weeks ago on spin 1 fields. And sometimes it's referred to as a dark photon. And I'll note that here we're thinking about, a lot of what I'm going to talk about is just the field theory of a massive spin 1 particle in curved space. But the eye, of course, is towards thinking about this field, eventually as being dark matter. And so, in fact, if you look at the literature, the vast majority of literature on dark photons is focused on the dark photon as a mediator with some other particles serving as dark matter. Here we're thinking about the dark photon itself as being the star of the show. And I should mention historically, this is known as the Prokop field, and I will sometimes refer to it as such. And I'll mention there's there's some overlap with very nice papers from October of last year talking about gravitational production of dark photons. So let's look at the Procca theory, which is the theory of a massive spin-1 particle. And in particular, I'm going to include the non-minimal possible gravitational couplings that can appear at mass dimension 4. So dimension 4 operators allow the symmetry of the problem. And in analog to how a scalar can couple with a xi phi squared r, this is how a vector field can couple to gravity. And nobody's done the full calculation, but you can sketch out how these things are generated by loop processes, and you can estimate order of magnitude what would be the size of these couplings that would come from loops. And the argument for why you should include them is essentially identical to that for a scalar, which is that for the scalar, it was realized in the late 60s that even if you set xi equal to 0 at tree level, if you start calculating loop diagrams, you find divergences that need to be canceled precisely by introducing a counterterm of this form. At low energies, you expect some imperfect cancellation. There should be some finite tree level value for this coupling at low energies. There's really no reason to ignore it and every reason to include it, also just based on usual intuition of effective field theory. So that we're doing the exact same approach here, but thinking about a vector field. Great. So let me get into the weeds just a little bit here. In general, I'm trying to give a broad talk here, but I want to get into the weeds just a little bit of the spin-1 to see how the important physics pops out. So I have this massive spin-1 particle. Massive spin-1 has 3 polarization states, 2 of which are your usual photon field, or these 2 transverse polarizations. I teach electrodynamics, so in the classes I teach now, photons propagating, electromagnetic fields are oscillating perpendicular to it. These are your transverse modes. And there's really nothing out of the ordinary which pops up here. Analogous to a scalar, I have some dispersion relation with a mass, and that mass gets corrections from nominal coupling that go like h squared. And there's one term that goes like h squared, and some terms that go like r. Nothing terribly out of the ordinary. But when I look at the longitudinal mode, this is like the scalar field that's hidden inside of this massive dark photon. What I find is, let's look at this first line here. This is for the longitudinal polarization state of this massive spin-1 field. I have a non-canonical kinetic term. And this is something which appears already if you just think of the field theory of spin-1 in flat space and the minimally coupled. So if I looked at this kappa, it would just be k squared plus m squared all divided by m squared. This is a totally, usually if you would go through this calculation as a homework problem, you would say, there's nothing particularly interesting about that. I can now canonically normalize my field. I get this, boom, done. But if I think about an expanding space-time, this process of doing the canonical normalization is actually a time-dependent function that you're absorbing here. And moreover, the mass that appears here gets corrections from the nominal couplings. And so what pops out is, so 1, I have this non-canonical kinetic term, which needs to have the correct sign, otherwise I'm going to have a ghost. And 2, the dispersion relation, once I perform a real field redefinition, has a non-trivial sound speed. And the sound speed is the ratio of these 2 mass scales in the problem, which is, we've denoted them mx squared and mt squared. And they're the mass combined with different linear combinations of the couplings. So I stare at this, you think hard about, for what values of couplings is this going to be a well-behaved, well-defined quantum field theory? Some things pop out to you. So first of all, I need this kappa squared, which appeared in the kinetic term of this longitudinal mode, to be positive. I need to have, I'll just finish the discussion of this plot, and then Philip, I'll take your question. This statement that kappa squared is positive corresponds to, if I look at high k modes, take the limit k goes to infinity, MT squared needs to be positive. So saying MT squared is positive guarantees me that high K modes are ghost free, are not ghostly. But I also have this sound speed. Non-trivial sound speeds has been something that's been intensely studied for maybe 15 years now in the context of inflation. Here we have a time-dependent sound speed. If we just enforce that the sound speed be positive at all times, that's the statement that mx squared and mt squared both have to be positive, both have to be negative. So what this plot is showing, I have these two masses in the theory. Mt squared, this is where inside this blue wedge is where it's positive. Mx squared inside this wedge is where it's positive. And the overlap of these two is this quite small region here where the sound speed is always positive and there's no ghost in the theory. If I move into this broader blue wedge, then I still have no ghost in the theory, and it looks like a perfectly well-defined theory, but if you evolve forward in time, say through the end of inflation, you can get, and what we're going to see is this sound speed is a not positive definite. So this is sort of a stability chart for the parameter space of the model. And that's what we're going to dig into for the next 5 to 10 minutes. Philip, you have a question?
Yeah, sure. When you wrote down that integral d3k, you were taking the Ricci scalar to only depend on time, on the conformal time, and not to depend on space. Otherwise, k wouldn't be a good quantum number. But when you have fluctuations, there's a fluctuation in the geometry.
Right.
And the Ricci scalar becomes spatially dependent.
So you have metric fluctuations, which would enter through R.
Yes.
Spectator field, the coupling to vector perturbations of the metric would come at higher order. It would be starting at like quartic order is how the vector fluctuations of the metric would be coupled to a spectator field.
Isn't the source of the Einstein tensor the spectator field? And if there's a fluctuation
so you source
in the spectator, there's a fluctuation in the Einstein tensor.
And then the back reaction of that is higher order.
Oh, okay. All right.
I'm going to write down an operator which has a vector field the vector perturbation of the metric has to be contracted with itself, is coming from a scalar, and the spectator vector, it's going to look like v mu, a mu. So it's a quartic order in the fields. So it's that, yes, this source is a vector fluctuation of the metric, and then you want to study how that vector fluctuation couples back to the vector field in the matter sector. That's a higher order process in the fields. So here we're doing a perturbation theory, but it's an excellent question. This R here is the background value, and you could say there's a dot plus dot here exactly, which would include the coupling to vector perturbations to the metric, and to scalar perturbations, the whole BAM. But all those things are going to appear at higher order in the fields.
Okay.
For example, we can talk about what is a curvature perturbation source by this, and it appears in second order in perturbation theory. But thank you for that question. Let's dig in a bit more into the stability properties of this theory. And so I pointed out that this longitudinal mode, which is relatively pedestrian in the context of flat space, ends up having this non-trivial sound speed when you consider evolution in curve space. And it's extremely dependent on these new terms you get from the nominal couplings. So in this plot, we're showing, so this is an evolution plot, say cumulative adjustments. The top black line is the sound speed if I take the minimally coupled swim one. The minimally coupled has identically one sound speed. Now, if I turn on some nominal couplings, let's say red, here's some couplings that for this mass scale is non-ghostly, but it's outside of the mx squared positive region. I get the sound speed is this red curve. It's going down, basically down to -1. So that means I'm getting a negative k squared term of my dispersion relation. Now, but if I ramp up the mass, or I could make the coupling smaller, or I could ramp up the mass, and I move out of this negative sound speed region, I pull up the curve and I end up with blue. So this is just changing the mass from 0.1 to 0.03. So there's this delicate interplay between the mass and the couplings. And you're always looking at couplings of order m squared, which we can talk about more as sort of what you would expect based upon having spontaneously broken gauge invariance. You have the possibility of one, creating this ginormous instability from having a negative k-squared term dispersion relation, or you can tweak it to move to criticality or have this non-trivial violation of adapticity, which is going to come from this. And we're going to see that leads to dramatically enhanced production, but still stable at all times. So this is the main player in the show as far as spin 1 particles that are nominally coupled is concerned. So you don't have to take my word for it. That negative k-squared term and these parameter stuff all work out the way it does. You can just put in these, write up your ODE solver for the equations of motion and study k-modes and hit play for different parameter values. And what you find here really is that red is the minimally coupled case, where I have, and this is the spectrum of particles as a function of over values of k. And this is by spectrum, I mean, I solved for the mode equations of alpha to late times, and I'm calling particles is defined by the Bogey-Bob coefficients at asymptotic infinity at late times. Red here, you get some peak, and then it goes down, goes all the way. It will keep going down and down as you go to higher k modes. Blue is what we refer to in the paper as runaway. There's many potential names you could give this. But here we're considering this is the same, or slightly different parameters than the last plot, I suppose, but this is a set of parameters where you're getting a negative sound speed. And what this drives is that the high k modes, this doesn't turn over. And if you can keep going to higher and higher k, it gets more and more computationally expensive to solve, because these things, when they're deep inside the horizon, are oscillating wildly fast. But this thing, if you're willing to expend that computational power, goes up and up and up and up. This is the runaway production that results from having this negative sound speed. And as I mentioned, so this is a very preliminary plot, which is going to appear in our follow-up, where we're thinking about parameter space that gives the correct Marek density. So as I mentioned, you can take some set of parameters. Here, dashed is the nominally coupled, and solid is minimally coupled in colors represent masses. Red here is an example that shows runaway. If I just tweak up the mass, mu is m over h, m scaled to Hubble, I can make this now convergent, say in k, but dramatically enhanced relative to the minimally coupled case. So using this interplay of the mass and these nominal couplings, I can get a dramatic enhancement of particle production during inflation. And so this is the story of spin 1. Maybe I can pause for 1 minute and we can take any questions about this. And I'll say one of the things I'm going to conclude with at the end of the talk is a question of how does UV completion change this story, if at all. So maybe that obvious question we can postpone to the end. But that's the most interesting question, I'd say, and I'm happy to talk more about it. Okay, there's no questions. I want to now shift gears, but only slightly, to think about another representation of a spin 1 field, which is the Kalber-Monde field, first discovered in the context of string theory. Similar to how A mu is the electromagnetic potential of a point particle, B mu nu is the gauge field of a string. But later on in context of string theory, people discovered D-branes, particularly in the mid-90s, the second superstring revolution. People realized there was higher form fields in string theory. I want to focus particularly on this B mu nu field. And this is an anti-symmetric tensor. It's a perfectly well-defined 4D effective field theory. I don't need to use the word string theory at all to talk about this thing. What we should keep in mind is that this is a spin 1 field, and I'll maybe sketch out a quick derivation and prove that this is true. But anti-symmetric, it's an anti-symmetric tensor field which propagates 1 vector degree of freedom. It's most well known as being an axion, which is if this field is massless, then here H is the field strength, star is Hodge dual, so it means contract field strength with a epsilon tensor. That whole thing is a vector. That whole vector is like the derivative of some axion. This is called the Calvert-Moan axion. You can just do this field definition and pop into the action. So here I wrote the action in terms of differential form notation. Take star H is partial mu phi, ignore the mass term. This just becomes the action of a scalar field. And this scalar field is known as the Calvert-Moan axion. But the Calvert-Moan field doesn't have to be massless. And what happens when the Calvert-Moan field becomes massive is that in addition to this pseudo-scalar degree of freedom, you now expand it outwards to have a whole vector degree of freedom. And in fact, the reason for discussing this at all is that it's not a vector like the Proca, it's actually a pseudo-vector field, which if you think at all about you look at the parity properties of the different things going into the theory, or even just think about the fact that in massless case, I'm getting a pseudo-scalar, not a scalar, you can appreciate that this, the vector field that I get out of the massive K is not a usual vector, but a pseudo-vector, so it has opposite parity properties. You don't have to go this duality route, and I can explain what this star means, this duality applies on shell. You can instead just work directly with the Calvert-Moan theory. You go through the exact same process as we did for spin 1. You decompose a field and then get finally to polarization states. The detail I would just mention is that where this vector degree of freedom comes from is I take the spatial components Bij, decompose them with this is anti-symmetric spatial matrix. I can decompose it into one vector. This Bk is a pseudo vector, or pseudo is spelled incorrectly there. This is your like pseudo Proca that lives inside Calvert-Moan. And there's a longer discussion we could have just about degree of freedom counting, about why is it that that you're only getting a vector field out of the Calvert-Moan. The one-line answer is if I take the equation of motion from massive Calvert-Moan, take a derivative of it, I get a constraint equation. If this was a gauge field, this was just an A mu, the usual spin 1 thing, I would get one constraint equation. For Calvert-Moan, I in fact get a constraint equation for every index in this, we have right here, every index row. There's ostensibly 4 constraint equations. Turns out one of those is redundant. You have 3 constraint equations. B mu nu itself has 6 degrees of freedom. If I kill 3 by 3 constraint equations, I get 3 left. Those are the 3 polarization states of NASA spin 1. So let's start by thinking about the gravitational particle production and the analog theory for Calvert-Moan. And you have the 2 possible couplings that this guy could have at dimension 4. And we call these new parameters Xi 3 and Xi 4. We go through the exact same, somewhat tedious but straightforward calculation. And you discover that there's a direct mapping, which is just proportionality of the Calvert-Moan effective theory, once I think about the longitudinal transverse polarization states, to the regular Proca. This is just a rescaling of non-minimal couplings. So the story will run our GPP ports directly over. If you ask the question, so how do I know if I have a Calvert-Moan versus a spin 1 field, if their gravitational production is identical? Well, let's start to think about other production mechanisms. This is what our whole paper is about on the Calvert-Moan field, but I'm just gonna very briefly give one example. If you think about a freeze-in production, where I couple the gauge field to the corresponding fermion current, and here I'm coupling to the current of the electron field. So the electromagnetic field, A mu, coupled to some J mu, and you can go through, this is a whole story of really charged dark matter. I can have some small coupling here. The analog to this would be to take B mu nu is this alpha gauge field, couple it to the corresponding current of a fermion field. The corresponding current would be the anti-symmetric matrix J mu nu, where there's a commutator of gamma matrices inside of here. And what's interesting, and I'm happy to give another talk on the exact physics behind how this works, but is that there's this opposite trend. And here these lines is showing this is the space of coupling versus mass to give the correct Rayleigh density of dark matter. Blue is the dark photon, the proca. Black is the copper muon. And the detail I'll point out is that as I go to lower masses, this curve is going down for copper muon, which means lower masses need smaller couplings to still get the same production. There's an enhancement of production of light copper muons. For dark photons at high masses, I need stronger coupling. There's a suppression of coupling for heavy dark photons. There's a suppression of the production of light dark photons. And that is a combination of, when I calculate the density, there's a mass going into it, but then there's the mass also enters into the actual cross section for production. And we can talk more about the physics of that, but you can trace it all back to the fact that A mu, J mu here is a conserved current. The current that A mu couples to is conserved current. B mu nu, J mu nu, this is just some term that's going to appear in the effective field theory. This is not, J mu nu is not itself conserved current. So this is all I wanted to say about the copper muon, is that the story of spin 1 doesn't stop with dark photons. There's other representations of spin 1, so higher rank form. This is a rank 2 tensor that is propagating a spin 1 degree of freedom. It turns out to be a pseudo vector, which itself has some interesting implications in terms of what are the things it could couple to. B mu nu is an anti-symmetric matrix. What it's going to couple to is J mu nu, and this leads to differences at the level of other production mechanisms and other signatures at colliders. But the level of GPP, in fact, so far as we've studied, it's identical. Okay, I think we're doing okay for time. The next thing I want to talk about, another case study here where actually the story is going to pop out to be quite similar, is the Arita-Schwinger field, which is spin 3/2 field. And in a more modern context, we usually think of this as being gravitino in the context of supergravity. But at this point, are there any questions?
May I? This is Jim Gates, Evan. I have a question.
Yeah, you.
Hello, can you hear me?
Yeah, I can hear you. Please go ahead.
Okay. My question, since this is the second time you've referenced supersymmetry or something related to this talk, can you just, is there a well-defined motivation for high spin that you know that's independent of supersymmetry? Well, in particular, independent of string theory.
Motivation for higher spins that's independent of string theory. Well, I mean, yes. In condensed matter context, you can have composite degree of freedoms with higher spin. But also in sort of standard model physics, there are already, higher spin baryons. Okay,
I'm sorry to interrupt you. I mean fundamental because
fundamental. I mean,
yeah.
But what's fundamental to one energy scale is composite to another one, right? I mean, if I was restricted to low energies, if I lived in the 1920s, I would think a proton is fundamental.
Okay, thank you. Okay, I got your point.
Just one final point there is, one thing that's mind-blowing is if you have these dark matter detectors.
Excuse me, there is a question from chat. You're asking to show more information about the slide number 15. Could you, I don't see the numbers of your slides, but maybe you...
There are numbers of the slides at the bottom. So
here, okay.
It's a section heading. But let me just finish that question from Jim, which is a great question, motivation for higher spins. The final thing I just want to comment is, and you're right that this is not a motivation for fundamental higher spins, but people are building giant dark matter detectors using liquid xenon. If you look at liquid xenon, it has a stable isotope that's spin 3/2, and it's something like 30% of xenon is this spin 3/2 isotope. Which is just information you can find on Wikipedia. So nobody's exploited this yet. These higher spin degrees of freedom that just exist as isotopes, and I could excite them by interacting with, say, some fundamental higher spins. But I think that's a really interesting direction. Okay,
So
slide.
may I comment? I mean, so I think if without string theory, there is no fundamental uh, motivation, right, for higher spins. I mean, your example is fine, but it is again some composite particle, but not a fundamental particle. So if you remove string theory, there's no way we can motivate higher spins.
Yeah, I think string theory is the motivation for fundamental higher spins. And I think
Okay.
as you can prove, yeah, this is a broader discussion, but this is a really interesting question.
Well, there is another question one can ask is, okay, let's forget about theory, but is there any observational motivation to have higher spin particles? So
in the standard model, you have baryons, different zoo of
yeah, but
baryons spin, and I could consider a dark sector where those are all stable. It's like really easy to do that.
well, it's not about easy. I mean, does the observations about dark matter anything suggest really need to have a higher spin? I mean, without the need of other motivations from string theory. So that's there are two ways one can question. Indeed, as you said and agreed that without string theory there is no motivation. But
So, can I just give a
yeah.
one sentence
Yeah.
answer to this, and then I want to keep going. I have a separate talk on higher spins that I give based upon work that I did with Jim, and high spins is something I'm really interested in. My one sentence answer is, this is the toughest question, which I do not have a strong answer for. A dark matter pheno person asked me this when I was at a birthday celebration or like lifetime achievement celebration for Rocky at Chicago last year or 2 years ago now. Dark matter pheno person asked me, if higher spins exist, why is it that every particle that we know is not? It would seem odd if there's no fundamental obstruction to a spin 35 particle, and yet every particle we've discovered in these like breakthrough after breakthrough, Nobel Prize after Nobel Prize is just spin 0, a half, and spin 1. I don't have a good question to that, and a good answer to that. And I guess my default answer though is that, but we haven't discovered dark matter yet. So maybe it's time to think outside the box. Yeah, that's all the time I want to spend on that question. I love that question, and I'm happy to talk more about it. What I want to talk about for the remaining time is Schwinger, comparing and contrasting with spin 1, maybe talking a bit about supergravity, but I'll try to not be too technical. And then just open questions for this field as a whole. And we can talk more about slide 15 afterwards. This is good. I appreciate the questions. Okay, let's think about the Schwinger model, which is a spin 3/2 particle, predates supersymmetry and supergravity, but it turns out that the Schwinger field is itself the superpartner to the graviton in supergravity. And you have this this action here where psi mu is a vector spinor field, has a vector index and a spinor index. Here I'm only writing the vector index. You go through a tedious and somewhat straightforward calculation to decompose this field into helicity states. Similar to how spin 1 had, massive spin 1 has a spin 1 degree of freedom in it and a spin 0. The massive spin 3/2 has a, properly speaking, helicity 3/2 states and helicity 1/2 states. And analogous to the dark photon, you get for the longitudinal mode, which in this case is a spin 1/2 particle, you have a non-trivial sound speed. What differs from the spin 1 case is that this is for the minimally coupled case. Already minimal coupling, it's a feature of curved space, and if I have a time-dependent mass, then I can get a non-trivial sound speed of this particle. So if I just set HR to 0, this would just be some, this would just give me 1 in flat space. But I might consider the Ricci square is non-vanishing, H is non-vanishing, just going through the calculation of this decomposition in curved space, and doing the field redefinition to canonically normalize my longitudinal mode, you again get a sound speed, which is non-trivial even in this minimally coupled case. We haven't ventured to do any non-minimal couplings. And you can go through the calculation in supergravity. And so I should mention, this is all appeared in a couple of papers I wrote with Rocky and Andrew, now I guess a couple of years ago, where one of the things we did was have this very nice compact expression for what is the sound speed in supergravity, the sound speed of the longitudinal mode of the gravitino. Here, phi dot is a vector of the scalar fields which are evolving. F is, if you're not aware of how supersymmetry works, it's a vector which corresponds to how is each field itself breaking supersymmetry. So if dW is non-zero, that means you're breaking supersymmetry. Each field can be contributing to that. You get a vector. And so I have a vector, which is how the fields are evolving, a vector, which is how is supersymmetry being broken. And it turns out that it's the combination of these two things and the angle between them that tells you, so theta here is the angle between these two vectors, which tells you what is the sound speed. And this is consistent with expressions that we found in the supergravity literature going back to the 2000s, dramatically more compact. And it's also consistent with early observations that people had that gravitational fields can propagate with the longitudinal mode, can have a sound speed that is less than 1. And you can, if you stare at this equation, you can convince yourself that it's manifesting between 0 and 1. So similar to the Proca, this sound speed can vanish. In this case, it's confined to be between 0 and 1, but there's nothing stopping it from hitting 0. In particular, if I just take a constant mass field in an F for W spacetime with a constant equation of state, you get a relatively simple expression for the sound speed. If I take W's 1/3 for radiation dominated universe, and if I consider sub-Hubble masses, I guess here I'm saying that mass less than 1/3 Hubble. At early times, everything is hunky-dory, you have some constant sound speed. So propagate forward in time, eventually at some moment, this numerator is going to cancel. And you have a vanishing sound speed. And then at late times, everything, again, when H is going to 0 at late times, I'm just going to go to sound speed equal to sound speed equal to 1. But there's an intermediate time in just a radiation-dominated universe, which is the most vanilla cosmology we can consider, where the sound speed vanishes. And this is specifically to fields which have gravitational fields which are sub-Hubble. Now, if we look at this in the context of inflation, the sound speed can vanish again, and typically around the end of inflation. So here's a plot of CS squared for 3 different masses. And again, it's really a phenomenon of light gravitinos, and in particular, lighter than Hubble. And most precisely, the Hubble parameter at the end of inflation. Here is the top. This is mass relative to Hubble of 0.01. It's hitting 0, boom, 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 boom. If I make it a bit heavier, it just hits once. And if I make it heavier, now that the 0 touching is lifted, now it's only going down to like 0.4. So how can we understand the quantum field theory of this? This also applies to the Proca field. All right, just think about a boson. So the mode equations for this fermion is actually an incredibly complicated system of fermion degrees of freedom rotating into one another. But let's just think about a boson with the sound speed and think about adiabaticity. If I take the simple dispersion relation for a scalar, I calculate the adiabaticity parameter and evaluate that at the moment, assuming CS vanishes, the only thing you get left is H over M. And for the gravitino, this is CS can only vanish if M is less than H. Adiabaticity is always order 1 then for the gravitinos, which can have a vanishing sound speed. So for a gravitino, and this is somewhat unique to the gravitino, the sound speed vanishing implies violation of adiabaticity. So let's think about what happens if you just plug and chug and calculate particle production. Circa the late 90s, people were doing this in the context of supergravity, and there's something known as a gravitino problem, which is an overproduction. It turns out that if you have supergravity with a single chiral superfield, then the field evolution and the SUSY breaking are always aligned. It's in 1D. This is a 1D2 vectors in 1D are always parallel. And you get sort of expect from studies of gravitational production around that time, you get some at some peak, and then at high K, you start getting oscillations where you're really probing the oscillations of the background. There can be also interference between different processes. The structure of these oscillations is a whole talk in itself, but the point to make here is that it goes up and it goes down. And the enhanced one is the longitudinal mode. Now, if you do the same thing, though, let's say there's a constant mass field, constant mass Fourier Schwinger, sort of one of the simplest EFTs I can write down, just like for the spin 1, here driven by these vanishings, these zero touchings of the sound speed, this curve never turns over. And it's driven by the this vanishing sound speed, right? Essentially costs zero energy to produce a k equals infinity mode, if only for a moment in time. And as I emphasized earlier, if I back off from this unstable region, I can get a well-defined, well-behaved quantum field theory where I have enhancement of production. And this is relevant to dark matter. And that the follow-up paper, which will map out the parameter space of dark matter, has been long to appear, but eventually it will come out when we get our act together. Okay, there's only 10 minutes remaining. Let me give some open questions, a quick summary, and then we can transition to questions after that. So first of all, let's think about, are there ways out of this runaway? So we're thinking about, effective field theory. Are there other terms in effective field theory which could stop this? If I instead think about, what if I just consider the fact that there should be some UV cutoff, to consider brute force cutoff for this EFT? Does that in itself save the day? Or maybe UV completion will save the day in the way that you have divergences and scattering amplitudes and quantum field theory coupled to gravity, but they can be resolved by embedding into string theory. Or maybe if I modify my gravity theory and some other way, I can resolve this. So let's first think about, what sort of UV cutoff would I need to completely remove this runaway for the spin 1 field? Well, this is all happening for fields that have massive order Hubble. It's happening around the end of inflation for modes that are exiting the horizon around the end of inflation. If you want to demand that the dispersion relation is positive definite for all k, the modes you need to be omitting are essentially, this is corresponding to some cutoff, which is of order Hubble, which is like patently absurd if I want to be studying quantum fluctuations during inflation. So the negative sound speed instability is relevant for modes, which would really ostensibly be describable by EFT during inflation. Otherwise, you sort of have to completely abandon this. So, okay, go a different direction. The UV cutoff in itself doesn't save the day. What about UV completion? So the simplest UV completion you could write down would be an abelian-Higgs model. And you can go 2 routes here. One, you can go directly to the symmetry broken phase of the abelian-Higgs, and I get some interactions. It's sort of straight out of textbook quantum field theory. The story doesn't change. There's no symmetry to protect you from these interactions. Same thing, I can write down directly a gauge invariant. And by gauge invariant, I mean the gauge symmetry is linearly realized for this, the U1 gauge symmetry. In terms of the Higgs field, there's nothing stopping this term from appearing in the action. And if I go to the symmetry broken phase, I get exactly the coupling. So there's the UV completion in itself does not save you. And then finally, maybe you could modify gravity. The same story happens. You need some modified gravity, which somehow forbids a vector field from coupling to, for example, the Ricci tensor. There isn't a theory like that on the market. And unless you have some express new symmetry principle which would do that, even if you set this coupling equal to tree level, you expect it to be generated quantum mechanically. I mean, and even if you just have symmetry scalar, just have a quartic self-interaction of A mu, which is allowed once A mu has a mass. Why wouldn't I include self-interactions? Then I can write down loops which will generate these couplings, just like for a scalar. So the there's no, seemingly fundamental reason to restrict these parameters to avoid the runaway. It seems to be something which you only discover by looking at cosmological spacetimes. Okay, let's go to some more broader open questions, which I think is, so a lot of what I work on is dark matter production mechanisms. In particular, I'm interested in non-thermal production mechanisms for dark matter. So that's focusing on sort of the beginning of the universe instead of what's going on today. So how can we possibly test the mechanism by which dark matter was produced? I think the zeroth order answer to that is when you study the production mechanism, you're mapping out the space of mass and couplings that could explain the relic density. That's like just the starting point. So then if somebody goes and builds an experiment and looks for those things, you can tell them this is the mass range which is allowed, and this is the couplings that are needed. This is the theory prediction for the mass and couplings. So if experiment measures, say dark matter has this mass, and I could, if only, let's say it doesn't measure any couplings, say it just has, part of which experiment says I have dark matter with this mass, you can pin down, is that mass possible in the context of this theory in order to get the right relic density? It is ubiquitous, but also somewhat constraining in the context of a single model, what range of masses are possible. And it's something which nobody has dug into, has been on my back burner for a while, is to think about this plot of n versus k, particle number versus k. If I evolve that forward to today, this corresponds to the velocity distribution of dark matter. And if I'm producing it thermally versus non-thermally, I have a thermal versus a non-thermal velocity distribution for my particles. And this impacts, when I do direct detection constraints, you have excitation value sigma v, the velocity average cross section is what's entering into this. And the direct detection constraints depend on what I assume for the velocity distribution of dark matter. Now, it's a very difficult inference problem to say what type of measurements would I need to infer the velocity distribution of dark matter, but I think that's an inference problem which deserves some attention. But really what I think is the most promising direction is similar to multi-messenger astrophysics, sometimes I call it cosmological complementarity, is that these inflation, and in particular inflation with dark matter production, has correlated observables. So for example, the models of where you can get the right relic density of dark matter, it generally is inflation models that have an observable scalar tensor ratio. You can get down to R's like 10 to the minus 5, maybe 10 to the minus 6, which is not observable, but it's up there. But arbitrarily small R, like R to the minus 10, just because of how the abundance at the end of the day of dark matter, we can talk more about this, it scales with Hubble, because I'm producing particles of massive order Hubble, so the relic density inherits this as energy scale. If I want the right relic density of dark matter, it's basically impossible to do it with very low R inflation models. And in addition, you also have the cosmological collider signal with non-Gaussianity. And also in these models, the isocurvature fraction can range from ruled out to you're never going to observe it. So there's some freedom there. There's a parameter space of isocurvature fraction. You could imagine a future experiment discovers there's a non-zero isocurvature fraction, which would be amazing, but I would never make that bet. But I think that there are these correlated observables in a given model, which I think is sort of the path forward for testing what particle species are around during inflation, and if there was huge particle production events, how are we going to know about it? But with regards to, honest to God particle physics, I'll note that there is pretty recently starting to be a direct detection effort for super heavy fields. So if I'm producing fields of order Hubble during inflation, the most naive expectation is these should be really heavy fields. It turns out you can get through these instabilities much lighter fields. So the gravitational production is not limited to super heavy, but in its simplest incarnation historically, we think about gravitational production as producing WIMP-zillas. And it's fascinating to me that, and very timely, that this is actually a hypothesis that we're starting to be able to test with experiments. An aspect that I've looked into with James on this call, along with Leah Jenks, who's the lead author. She's now a postdoc at Chicago, and Konstantinos Kochilikos and Swan Alexander at Brown, is thinking about these direct detection experiments for higher spin fields. And we want to know to what extent can I discriminate spins, if I look at the angular dependence. So the whole program of cosmological collider applied to higher spins is that angular dependencies encode the spin. So here we're looking at directional direct detection, some spin S or S plus a half field comes to the detector. It turns out that there is some characteristic angular dependencies which distinguish the spin in direct detection experiments. I think this is probably wildly futuristic, and it's above my pay grade to really speculate on our next generation experiments actually going to observe this, or is that pie in the sky thinking? But at the very least, I think it's moving in the right direction of how do we pin down these sort of like new dark matter models from experiments, not just cosmology. All right, in my 0 minutes remaining, let me just summarize here. I think gravitational production of particles, meaning it's just nothing but the non-adiabatic expansion of space-time. That's the only ingredient. Every field is coupled to gravity. That's the equivalence principle. So I think it's simple. It's minimal in terms of model building, and it's ubiquitous, meaning model X has this phenomenon for like this swath of parameter space. This swath of parameter space gives me relic densities of order the observed one. I think it's interesting that seemingly simple, say, relatively pedestrian models can give you these very dramatic instabilities. And so the purpose for understanding those is now I can back off from it and understand in what regions of parameter space is particle production enhanced, which really opens up the allowed mass range. So it's not just pinned at m equals Hubble. There's a significant range that's opened up by these instabilities. I think there's a lot to do still in this research direction on the Cosmos side, and on also thinking about high energy physics experiments of dark matter models generally, which pop up when you think about gravitational production. So that's it for today. Thank you for joining, and I'm happy to take questions.
Okay. Thank you very much for your very interesting talk. Please, questions. Please ask questions. I saw some question in chat. I see a question in chat. This is about the sound velocity. Who is this? Questions from Mikhail Nardelli. Maybe you can ask just now your question.
Or I can ask the question.
Okay,
or Mikhail, you can feel free.
Mm-hmm.
But it's a great question. It's that can C squared be equal to 0.9? Yeah, absolutely. 0.9 is a perfectly good number between 0 and 1. Is there a slide 18? Yeah. Was there a reason for 0.9 as being a special number?
Mm-hmm. I cannot hear you.
Do you hear me?
No. Yes. Well, you finished to answer or not yet?
Yeah, I'm finished. Okay, there's some raised.
Okay, because there are a couple questions. Shravan, could you please ask your question just now?
Hi, Ivan. Ivan, I don't know how to pronounce Ivan or Evan. Sorry. Anyway, my question. Thanks for the very nice talk. So, my question is related to the sound speed. Well, in cosmology, we construct theories to have sound speed and between 0 and 1. Basically, we don't want superluminal or any instabilities. Suppose we construct a theory which is like this with a good range of sound speed between 0 and 1 for cosmology.
Mm-hmm.
But then we apply the same theory in a different context, in a different space-time, for example, black holes.
Mm-hmm.
Can we say the theory is still healthy? So suppose if the theory turns out to be good for cosmology, and then the same thing you apply in the different background, if it turns out to be bad, then it's better to throw away the theory, because we want to construct theories good for any background, not for a particular background.
So that exactly. So for this gravitational sound speed thing, so we even promoted it to a swampland conjecture that theories where in the sound speed theory, supergravity theories where in the sound speed vanishes, or you can generalize it to if I have multiple interacting gravitational-like fields or these things, the determinant of a matrix of sound speeds vanishes, that theory's got to be in the swampland. Because if it is pathological in one background, like it shouldn't depend on the history of the universe or the existence or non-existence of black holes, whether I can consider this field theory. Like there's got to be underlying fundamental principles which tell you what field theories pop out at 40 effective field theory level. And then cosmology shouldn't dictate that fact. There's got to be some fundamental underlying principles.
Okay.
Thank you.
I see a question from Philip. Philip, could you please ask your question?
First of all, thank you for this very interesting presentation. My question's in two parts. There was a discussion a little bit earlier about whether there should be elementary or fundamental particles of spin higher than 1. Well, we're all in agreement that there's a graviton, which is spin 2. So spin 3/2 is less than 2 and would not seem to be not allowed. But if there are such particles, why wouldn't they be produced thermally? Why do you have to go to this mechanism that you've introduced? Would that enhance it over thermal production?
It's the naive expectation, they should be like a free field theory. Writing down interacting higher spin fields is like one of the greatest challenges of modern theoretical physics. Jim Gates on the call, Professor Jim Gates, is an expert on that. But historically, it's always been believed that if you had higher spins, that has to be a free theory. At the minimal level, though, we know everything has to couple to gravity by the equivalence principle. So the motivation for studying this is let's take the minimal possible interaction, which is that to gravity, and think about that as driving the production. I'll say there is a paper which studies thermal freeze out and argues that within like a physically well-motivated range of couplings and things, you can get very low density. So it is not restricted to that. This is where my biased perspective took me, was thinking about gravitational production. I mean, the other reason is that higher spins have to satisfy the Higuchi bound. This is a broader discussion. You have this thing called the Higuchi bound, which is a bound on the mass as a function of spin. It's basically m squared is bigger than s minus 1, h squared. So they have to be bigger than Hubble. It's difficult to have particle production in this super heavy regime. The only way we traditionally know to produce these particles that are bigger than the Hubble parameter in the early universe is through gravitational production. That's what Rocky called WIMPzillas in 1998. So that just the mass range that you're confined to naturally motivates gravitational production.
Okay. There is a question from Richard Kerner. Richard, please ask your question.
Yeah, I remember that some time ago, Fred Hoyle argued that for maintaining steady state and constant density, it's enough to create 1 hydrogen atom per cubic kilometer per year. Do you think it's possible to attribute such a thing to gravity?
Sorry. You're saying back to the steady state part? Sorry, what is the beginning of that?
Fred Hoyle argued that steady state can be saved if you admit that there is creation of matter. There is inflation, but creation of a constant density. 1 hydrogen atom per cubic kilometer per year is enough.
Yeah. That's here though. It's the expansion of space which causes the production of particles, which actually Schrodinger first pointed out in 1935.
Yeah.
Called paper, I think, called like the proper vibrational motions of a string in expanding space-time or something. He's considered like an elastic. Effectively, though, in sense he's studying quantum fields. anchored space. So it's the expansion space which is causing that. So no, I don't think we could end with somehow relate this back to a static.
One can imagine Big Bang, and after Big Bang, entering steady state.
Yeah.
Yeah, maybe.
Oh.
Richard, you can roughly describe steady state as a de Sitter geometry, which is inflation.
Yeah.
And you can describe Hoyle's C field for particle creation as the graceful exit.
Yeah.
So it's not, I mean, in a sense, that theory might be relevant, but only in the very early universe. Hoyle wanted it to be relevant today,
Yeah.
which was difficulty. But with inflation, I think you're right. I think you can revisit the steady state theory.
Yeah.
Also, I mean, dark energy is inflation round 2. So
yes,
that's right now. But that's
Thank you.
an interesting perspective that had not occurred to me, and I definitely need to think about that more, though.
Thanks.
Okay. More questions? If there is no more questions, maybe I will ask the last question. Since you consider Rarita Schwinger, and Rarita Schwinger, of course, is related with, for people who are doing super gravity or super string is related with supersymmetry. Is supersymmetry is important? Is supersymmetry play some place in your consideration? What do you think? Is it important or it does not important in your approach? What do you think?
I mean, we know supersymmetry is broken during inflation. And so everything I presented today was sort of assuming a hierarchy between the SUSY breaking scale and physics at the inflationary scale. But I do think actually studying supersymmetry is extremely well motivated. I think if the way to discover supersymmetry is going to be looking for correlated observables in inflation. So I have 2 papers, or I have 1 paper actually, I guess, with Jim Gates, who was here, about this very point. What we're arguing is that like from inflation, the pattern of non-Gaussianity, it encodes the mass spectrum of the theory and the couplings, and there's some like shadow of supersymmetry, which I can disentangle by having this like signature of fermions is X, signature of bosons is Y. There is like corrections too, but at tree level, they have equal masses. And so just supersymmetry also tells me, for example, with higher spins, it tells me what fields exist. And that itself is already a lot of information. So I actually think that, while I didn't talk about it today, I think the path of discovering supersymmetry goes through cosmology. And that's an example of where you get correlated signals.
I think there's another way to address Irina's question. The question is, what's the mass scale of supersymmetry breaking, and how much of the omega matter equals 0.3 can we attribute to supersymmetry? Now, for the moment, we can only set a lower bound on supersymmetry masses of about a TeV because of the non-discovery at the LHC. But I think, Evan, your mass range began at 10 to the 6 GeV, not 10 to the 3 GeV.
But SUSY would be broken by the energy density during inflation, though. So the SUSY breaking in the early universe is not the SUSY breaking scale today.
So what would you put as the mass of the lightest non-thermally produced dark matter particle in that case?
Of order the Hubble scale.
Today?
No, during inflation.
No, so what does that mean? Okay, in normal units, in GeV, what does that mean?
I think it's extremely optimistic to say it's near the TeV scale.
But all right, so would these particles be produced at the LHC in that case?
But okay, let's think for a second. Yeah, so I'm saying I do not, personally, my bias is I do not think supersymmetry is going to be discovered at LHC.
I'm sorry, your bias is
I do not think Susie is going to be seen at the LHC. No, I do
Oh,
not
yeah, no,
think.
but I'm not asking about Susie. I'm asking about all of the dark matter particles you've presented with us
Okay.
today.
So outside of the context, so within the context of supersymmetry, I do not think you're going to be able to see. I don't think that's my bias was a Susie breaking scale. The question more generally of implications of gravitational production for particle pheno. Can I get gravitationally produced dark matter down to the TeV scale? That's in general a challenge. So through Friesen production, you can get there. And it's a challenge for a number of reasons. I mean, there's like a growing small subfield dark matter people who consider dark matter in, say, the GeV, MeV region, which is extremely testable by precision electro weak. But you have to do a lot of cooking in the kitchen to avoid warm dark matter constraints. It's difficult to, when you start producing lighter things, it's hard to make it extremely cold. In the gravitational context, the momentum spectrum is usually peaked around Hubble. If its mass is much less than Hubble, momentum is peaked around Hubble. It's relativistic for a really long time. So you have to do, there's probably like a small viable region of parameter space where that can be true, that you would test models I talked about today at the LHC, but I don't personally consider that a promising possibility. I think it's more likely you want to look for rare but energetic recoils in direct detection experiments, things like that.
Okay. More questions, please? If there is no more questions, let's thank our speaker once again for very interesting talk. Thank you very much. Thank you.
Thanks.
You think you're more?
Yes. So the next seminar will be, in 1 week. Correct or not? Correct.
Yes, I remember, yes, in 1 week.
Okay.
What will it be?
Who's the speaker?
It will be more.
Not in 2 weeks, but in 1 week.
Yeah,
But
no,
Who's the
in
speaker?
1 week. Speaker is Enrico Payer from Cambridge. He might be mostly speaking about cosmological bootstrap and non-Gaussianities.
Yes, indeed. Enrico will speak next week, yeah.
Mm-hmm.
Yeah.
Okay. Okay. So thank you.
Bye-bye.
Bye-bye. Bye-bye.
Bye-bye. Bye-bye.
Send your slides so that I will upload them.
I will. Yeah, bye.
Especially Jim was curious to see them later.
Sure.
Yes.
Bye.
Okay. Thank you very much.
Thank you.
Thank you. Bye.
Alexei, what about to speak a little bit, not now, maybe in Saturday, about this memorial events to Alexei Stravinsky?
Better on Sunday.
On Sunday, what time is more appropriate for you?
Anytime, but just on Saturday I will be in the train for a while. Okay.
Okay, I understand. Sunday, any reasonable time in China. Okay.
Until midnight is okay. So until 7 p.m.
Okay, good, very good. Okay.
But okay, great. See you
Bye,
then.
everybody.
Yeah, bye.